Good afternoon. It's Thursday. We'll get the slides up. All right. So our journey started last December after BMO acquired Bank of the West. And in the middle of December, we took a trip to San Ramon, California for in-person workshops. And in between one of the workshops during the break, Sanjay from the Bank of the West team said something to me that really stuck with me. He said, we have only one shot to get this right. And he was absolutely right. Given the amount of volume and complexity and the different time constraints that we're working under, we did have one shot to make this right. So today, we will take you on a journey to explore how BMO, in partnership with AWS ProServe, migrated 1.8 petabyte of data warehouses and data marts to the cloud. So we will share with you our experience in these critical steps, right? So big migrations start with small steps. So we will share with you these small steps that we took that really set the tone for the rest of the migration. And we will also explain to you the design decisions we made and deep dive into the repeatable frameworks and repeatable architecture that you can take home with you. At BMO, we boldly grow the good in life and in business, and we're the 8th largest bank in North America. We have been serving customers since 1817. This Bank of the West acquisition is the largest acquisition in Canadian banking history, and this combined entity serves over 13 million customers in communities across Canada and the United States. And we're now the 10th largest bank in the US, and we have footprint in 32 states. And if you can't find a BMO branch in your state, we have digital banking across all 50 states. So 1.8, 24/7, and 100. So I want you guys to pay attention throughout the presentation, and there will be a quiz at the end. And if you get it right, Felicia here is going to give you a prize. And with that, I'll pass it over to Felicia.
Thanks, Mark. Hello, everyone. Welcome to our session. Again, thank you for being with us today on this very last day of reInvent. What an incredible week. My name is Felicia Iloa, and I'm a principal consultant with AWS Professional Services. Now, there's quite a few of you in the room today. I'm assuming you might be navigating your own migration journey. You might be starting your migration. Maybe you're in the middle, or maybe you just really want to hear about snowballs and migrations. In any case, you're in the right room. As Mark mentioned, our agenda today really is a blueprint. It's a roadmap of all the small steps we took along the way. Now, every migration is different. Ours, as Mark mentioned, took place in a post-acquisition environment. And for those of you that have done M&As or post-merger integrations, it provides a lot of timelines and technical constraints. However, we're fortunate enough to have the team that made that migration a reality with us here today. So from the Bank of Montreal, we have Mark Wong and Amy Sang. And from AWS Professional Services, we have San Barar. They're going to walk through all of and dive deep into the technical design and architecture and all the decisions that we made and share a lot of the lessons learned. But more importantly, provide you with insights into the partnership with AWS Professional Services. As a reminder, today's session's a 300 level, and if you have any questions, we ask that you hold off until the very end. We'll leave about 15 minutes just to walk through anything you had in mind and go through the quiz that Mark promised. So with that, we'll bring the BMO team on stage.
Who has heard of snowball before? Can I see a show of hands? Okay, about 1/3 or half. And who has used a snowball before? Just one person? All right, good. So we have a lot to tell you about snowball. So these are not the snowballs we're talking about. So the snowballs we're talking about, we actually brought one to the stage with us. So this bad boy is 45 pounds, and it plugs into your data center, stores 100 terabyte of compressed data. And just to put this 1.8 petabyte into perspective, so if we were to store it on DVDs, it'll stack up to over 1,500 feet tall. So that's taller than the Petronas Tower in Malaysia, I believe, right? And then taller than Willis Tower in Chicago, and also Empire State Building in New York. And if we were to transfer this over the wire, it's going to take over 3 years. That's because when we started the migration, the data center traffic speed, network speed, was 1 gigabit. So what are some of the challenges? So first is we're extracting from live systems. We're extracting from production systems. And we had estimated 6-hour window to extract. And when we first started this project, we plugged in multiple processes to extract. So plugged in the Snowball, and software was multi-threaded, downloading data into the Snowball. And it caused an outage. So we had to be very careful dealing with live systems. And second is the volume and complexity. So by complexity, I mean that we have 4 different data warehouse technologies we're extracting from. So Oracle, Teradata, Hadoop, and SQL Server. And from a volume perspective, when we started this project, it was 1.5 petabyte. And by the end, it grew to 1.8 petabyte. And we had over 1,300 schemas and over 144,000 tables. So as I mentioned earlier, the connectivity is very, very slow, right? So we can't do any online migration. So we had to use offline options. And from a discovery and due diligence perspective, before the acquisition was legal or approved, we couldn't do any technical deep dive. So the migration, the conversation really started in February. So why did we choose Snowball? Snowball wasn't my first option, actually. I thought in this day and age, there's got to be something better than this thing here. So we looked at DMS, and DMS required AWS infrastructure. And also, that didn't have an offline option, right? Remember, the network speed was slow. And then the other piece is that we wanted to rely on subject matter experts from Bank of the West. We also looked at database replication. So the data warehouses in Bank of the West exceeds RDS limits. And even when we moved that to the cloud, we still had to extract it out and ingest it into Redshift. So this seemed like mission impossible, right? So how do we overcome these challenges? So first and foremost, it starts with the people. So we had this one team mentality, working with BMO, Bank of the West, and AWS ProServe team. And we built trust and built the right roles and responsibilities from the very beginning of the project. And second is we selected the right tools, and we built reusable frameworks and automation around them. So the right tools I'm speaking of are Snowball, SCT, and Glue for ingestion. And last but not least is we set clear goals. So the goal is leave no data behind. We're taking 1.8 petabyte and moving it to the cloud. And the other one is we wanted to have 24/7 extraction, right? This window, 6 hours, we had to overcome that challenge. And the third is that we wanted to ingest the entire Snowball into the cloud in 1 day. So 100 terabyte in 1 day. So those are some of the goals we set. So I will pass over to Amy to explain in more depth the design decisions we made.
Thank you, Mark. Good afternoon, everyone. Now we selected Snowball as the way to migrate our data. The next step is to figure out how we're going to get the job done. Since we were still under merger and acquisition regulations, we couldn't access to systems, we couldn't access to data. So we started with high-level goals, as Mark mentioned. 1.8 petabyte of data to migrate. That's a lot of data. And we quickly figured out we couldn't migrate the data all at once. So we worked with our business partners, and we prioritized the data migration based on their need. Next, we want to run the extraction around the clock. And to do so, we have to automate as much as possible. Now, with the help of AWS Professional Services team, we automated the data discovery and data extraction. Then our source systems was still up and running in production environment. So to minimize the operation impact, we only have 6-hour windows every day to do our extraction. And that is not going to meet our goal. So what we did is we built a parallel environment to production, which allowed us to continuously extract data. Lastly, we have an ambitious goal of ingesting data daily, 100 terabytes, to support multiple business use cases, from financial reporting to AI/ML to regulatory requirements. And our first 100 terabytes took us more than 3 weeks to complete. But after numerous enhancements, we made it. And Sam is going to talk about how we were able to achieve these goals. But wait a minute, 1.8 petabyte, 24 by 7, 100 terabyte? Well, these numbers sound familiar to you? Yes, those were Mark's quiz question. Now we got our goal set. We need to look at the non-functional requirement. We have 6 guiding principles in mind to set the guardrail when we migrate to the cloud. And I want to highlight 2 of them that are particularly important in the cloud migrations. First, data security sits in the forefront. In addition to encrypt data in transit and at rest, we also encrypted sensitive data as we migrate to the cloud. It takes more time and effort. So why are we doing this? Well, first, we want to have added protection to the sensitive data that we have. Second, we are running in the federated environment, and we plan to share the data across business. But not all of the business cases require access to sensitive data. So with the encrypted data already available, we're ready to share with the business securely and consistently. The second guiding principle was we want to have a strong data governance. When we migrate our data, we want to make sure these data elements are available in our enterprise data catalog. And those data are searchable and discoverable through our in-house built marketplace applications. We built data validation framework to ensure that the data we migrate are migrated completely and migrate accurate. Now with these 6 guiding principles in mind, we're ready to put the plan together. Since we have a very tight timeline, we need to ensure that we have a well-architected execution plan, a well-orchestrated execution plan to maximize our migration process. When we look at our project, this project has 3 main functions: data extraction, data ingestion, and data access. And we want to run our migration like factory-style approach. We want to build knowledge as we go, and we want to learn from it, and we want to optimize our execution plan as we repeat this process. When we start our migration, we run into numerous issues. We have tables with no primary keys. We have tables and columns with special characters. We had a data skew issues, and we have white tables issues, meaning tables with more than 1,000 columns. And these issues slow us down. So we had to adjust our wait plans to continue to run our migrations while we address these issues in parallel. And our wait plan allows us to do that. Since we have multiple functional teams and a lot of moving parts, we want to make sure that each team understands what's going on in each other's space. So we created a daily cadence calls, including leadership. In that call, team will bring up the issues, action items, and we make a quick decision where we need to be, where we need to have. And we make this decision as we're ready, and then we keep going. Now, with this continuous feedbacks, functional teams will be able to continue to moving forward and make progress. Now, I mentioned about our wait plan. this is how our wave plan looks like. Since we are using Snowball to migrate data, and each Snowball, capacity of each Snowball is 100 terabytes, we want to make sure we ship our Snowball as the data is filled in that Snowball. So we define our wave plan by Snowball. As you can see, we have 16 waves. Yes, we did plan for 16 Snowballs. Then we stagger our wave plan so that when we complete the extraction of data in the first wave, the extraction moves to the next wave, while ingestion continues to happen in the first wave. So as you can see, we continue to run this in the stagger approach to maximize our timeline. Now we have goals, we have guiding principles, we have an execution plan. Putting all of these together, how does our end-to-end process look like? Let's dive into it. On the left-hand side, in our on-premise environment, we have source systems. We use AWS SCT to extract these data, put it in Snowball, ship it to Snowball, and unload it to our first S3 bucket. From there, we run a security scan and put it in a landing bucket. Then ingestion process starts. It converts the data formats to Parquet, and we encrypt the sensitive data. We also use a group data catalog to store our technical metadata. And we have a connector to connect to enterprise data catalog. And we store the business metadata there. And user will be able to access these enterprise data catalogs through in-house marketplace applications. Once ingestion completes, we store these data in the final S3 bucket, or we call distill bucket. And we use Redshift as our analytical platform, and we load the frequently accessed data into Redshift, while we kept the rest of the data in distill bucket. So essentially, we created a lakehouse architecture. And from end user's perspective, we enable the existing tools, existing BI tools and SQL tools to connect to data in Redshift. And users will be able to run ad hoc queries as well as reports. We also built MLOps data pipeline, and we enable Amazon SageMaker to connect data to Redshift for these data science use cases. Lastly, we use data sync to move our incremental data. I want to come back to this end user data access a little bit. We have large analytics communities across businesses and different personas, such as data scientists, business analysts. And each of them has a different access entitlement. So it is important for us to implement fine-grained access control. Now in on-premise today, we implement fine-grained access control using our in-house solutions. But over time, it became complex and difficult to manage as business requirements evolve. And from user experience perspective, it may take them multiple steps to get access, and it could be time-consuming and frustrating. So we took this opportunity to modernize our back-end data access provisioning process. What we want is self-service, user-friendly, at the same time enforce fine-grained access control. So let's dive into how we did it. In this example, I have 3 access groups by function: finance, another finance group which has access to restrict data, such as PII. Then we have a marketing group. We use AWS Identity Provider to federate these access groups to Redshift role one-to-one. Then we use Redshift role-based access control feature to define a permission for each role. It can be role-based, column-based, or both. For Redshift spectrum tables, we leverage AWS Lake Formation. And we implement access policies similar to Redshift RBAC. So far, so good. Now, to implement access on these external schema for these Redshift roles, we will need to create corresponding IAM role for each one of these functional roles, like finance and marketing. And that creates the next challenge. First, it creates too many IAM roles. Second, we hit the Redshift limit. In Redshift, we can only attach up to 50 IAM roles to the Redshift clusters to access other AWS services. So we brainstormed with Redshift team, and we came up with this solution. Rather than creating IAM role per functional role like finance and marketing, we create IAM role based on the data classification roles, such as general, PII, and then other data-sensitive roles. Then we attached these IAM roles to Redshift cluster. Then we grant access of these IAM roles to AWS Lake Formation. Now users will be able to access both Redshift local tables as well as Redshift external tables. Now, these unique solutions allow us to enforce fine-grained access control, at the same time significantly reduce the number of Redshift IAM roles required. And we will share this solution in AWS blog soon. Now, I mentioned about several automation processes that we developed as part of this project. We started small. We talked about automating data extraction using SCT, and then ingestion framework. I also mentioned about how we implement fine-grained access control using the data access framework we just built. And we use Snowball, offline device, to migrate large data volume. This is what we end up with. We deliver significantly more capabilities and patterns as part of these projects. Now, these frameworks will be repeatable, reusable, and foundational for our future cloud migrations. In fact, we have another project underway, cloud migration project underway, leverage many of these capabilities and patterns. Now with these scalable solutions, we can accelerate our cloud migrations. And we can also deliver the actionable insights to business faster, and then in turn, help business to deliver this exceptional customer service while driving royalty and growth of our business. Now I'm going to turn over to Sam, who is going to talk about some of these repeatable frameworks.
Thank you, Amy. Repeatable frameworks. Before we go there, let's go back to our data scope. 1.8 petabytes. What is really under the hood there? We're going to focus on Oracle and Teradata. It translates to over 1,300 schemas, 144,000 tables that we got to migrate. We use a couple of frameworks that we'll dive into today. The first three will answer our 24/7 extraction. Going back to Mark's quiz, remember those? Don't worry about reading the frameworks. We'll dive into that in a bit. Ingestion framework for 100 terabytes a day, and a data validation to make sure we validate our data 100%. Now, before going into this, let's take a little deep dive into AWS schema conversion tool. I know it sounds like a schema conversion, but it will help you migrate your data as well. What is it? It's a heterogeneous data migration tool. You can go from Teradata, or Oracle, to Redshift. That was our scenario here. Let's just walk a little bit of a use case. How do you typically do it? Right? As a user, you log into a Windows-based UI tool. That's your AWS SCT. Then the data is extracted by the AWS SCT extractors running on your Linux. You can have one or many. In our clusters, we had up to 9 extractor agents running. So as a user, first thing I would do is assessment report, right? It tells me is what I can do fast, where it may need to be more attention, and what things may need a manual conversion. Once I've done that, you can see a little bit of the UI there. You can right-click on it and start the extraction process. Fairly easy. Now that works, but keeping in mind we have 1.8 petabytes, 144,000 tables. We're not going to have somebody sitting from the UI and clicking it. We had to do things differently. First thing, coming back to the snowball, we are doing things offline. Second, AWS SCT CLI. So we want to move away from the UI and keep everything in code. This is probably one of the first projects exclusively using AWS SCT CLI. Second is we want to automate. We'll dive into these as well, SCT Agent Monitor, the SCT Orchestrator, as well as the SCT Project Generator. We'll dive into all of those in coming slides. So going back to our frameworks, it all starts with knowing your source. Right? So we created an inventory and metadata framework. It's a simple framework, set of SQL scripts that dive deep into our source, not just about like column names and schemas. We have those. We want to know your partitions, number of partitions you have, the sizes of partitions, so we can understand and learn where the SKUs are, how we can distribute some of those tables appropriately. And that is very important to our next part when we're building the SCT CLI projects, is categorizing our tables. So like I mentioned, I had 9 agents. Each of those agents have multiple threads running on them, and we want every single thread to be busy all the time. We're doing 24/7, but if a couple of our threads or a couple of our agents are idle, well, we're not really 24/7. We want everything to be 24/7, all our single agents. So we want to make sure our distribution is as even as possible. So small tables, large tables, those which get partitioned appropriately. So once you have that categorization, we create the SCT projects. We kept normally about 100 projects per wave. We try to keep it more projects and less tables in it. It's just easier to debug and troubleshoot. Okay, so that helps us create the SCT CLI. Just in case if you guys haven't seen what a project, SCT CLI project looks like, here it is. It describes about your project, your source, your partitions and filters you apply to it. Now we got our SCT projects. What do we do next? Well, that wasn't us, luckily. We're not going to have somebody running it again, right? We want the automation, 24/7. To achieve that, the first thing we need to do is to understand what's happening at every single agent all the time. So we record those about 7 minutes or about 1,000 log events. We record it to a centralized database. Once we have that, our SCT orchestrator summarizes that information and figures out what's happening at every single agent and overall, holistically, what's happening with our project. Is a particular agent failed or the whole project completed successfully? If it's a failure, it will send a notification. If it's a success, it'll pick up the next project in the queue and start it. So what did that help us achieve? 24/7 extraction. So no human intervention there. It just picks up the next project, starts it, and keeps extracting 24/7, even on the weekends and on stat holidays. All right, let's look into the ingestion framework a little bit. As Amy mentioned, our snowball comes in, it goes to our intake bucket. There is a security scan of all the data coming in from there. Once we have security scan done, our landing bucket, and that's really our ingestion framework is starting from. Right? We have a glue jobs that take that data, put it effectively into our data lake. Right? Now you'll see the client-side encryption. That's a key requirement. Like Amy mentioned, data security is a must. Once that there, a selective amount of tables will reach it to Redshift. Right? So the high priority tables reach to Redshift. Once that we have the data in Redshift, now it is accessible through Spectrum as well. When we do our validation, we don't just do it through S3. We want to do the end-to-end validation. Right? So that's why we go for a validation framework. We talked about that metrics database that was going on. It was also collecting things like number of rows. It was doing some statistics on it as well. So we validate against the source data or source metrics. Just like our SCT extraction, we had a lot of projects, a lot of configuration. We're not writing a lot of code. Even from ingestion side, for every new schema or every new table, we don't want to write code. So it's all configuration driven. We'll take a look at how we actually created those configurations. Now you need to orchestrate all this. That's where the managed Airflow service comes into picture. So from a user perspective, like Amy mentioned, they can access it through Redshift, also through the Spectrum. Now, Amy showed you a lot of other services that created, some of the supporting services that you create along the way. So your ingestion framework is a big one, but other things like schema creation, or you want to delete a particular partition because you want to have ability to, after your validation, if there's an issue there, you want to be able to rerun some of that stuff again. So some of the supporting services you'll create along the way. Okay, I promise we'll talk a little bit about how do we generate the configs, because it's all driven off the configuration. We don't write code, we write a lot of configurations that come up. The first is source. Right? You need to understand information coming from source. The business priority list, we talked about not all the data makes it to Redshift. That's the business priority list. Data classification, that's how we know what we want to do client-side encryption with. SCT emission list, now this is interesting. The SCT actually does not generate an emission list. What we found is, let's say if the SCT project had an issue, and we wanted to rerun the project, we wanted to clean up, because some of those things we were generating some like almost very small files, and then trying to clean them up in Snowball was taking longer. It was quicker for us to just ship it. Right? We had a little bit of room there, we shipped it, and when we came on the ingestion side, that's where we omitted those prefixes. We just didn't ingest them. So that's how the emission list came about. And of course, once the data lands, you do a metadata search on what you have, where you have the data there. You take all that information, you put it together. What kind of config are you really generating? There's a few things. One is source to target. Right? We have Oracle or Teradata. Here we have a Redshift, and actually we have S3 as well, so glue catalog. So that's your source to target mapping. So in our case, we're not only looking at the Redshift, but also intermediate glue catalog as well. And then the batch. We're not going to take all of the 100 terabytes or even 1.8 petabytes in one shot. It's taking the big data problem, putting it into digestible pieces. We had concept batches. In the batches, we also went further into saying, okay, what your partitioning key is going to look like in the S3, or your distribution in your Redshift. Since we're using Airflow, DAGs, if you guys are not familiar with DAGs, it's just a simple workflow. It'll tell you, okay, you start from here, you do X number of tasks, and then you move on to the next task, and that's when your success ends. That's what really a DAG is. So it's fantastic. We created our configs, we done our ingestion process, we have our DAGs, we're going to load those DAGs to Airflow. What happened? Okay, so we'll talk a little bit about optimization into it now. So first time we took all those hundreds of DAGs that we had, and that's a real shot from our logs. It was 99% CPU, just based on putting a lot of DAGs in there. So some of the optimizations that we had to do. Number one, local configuration files. So get all your configuration file that we had into local, remove the top-level imports in your Airflow. That's a huge thing. Small little thing, but it makes a huge difference. Remove the use of XCOM. So XCOM is like how, if one task is done, it needs to talk to another task. That's how the communication happens in Airflow. So try to reduce the amount of data you're passing through that. And limit calls to the other services. So after we did all those, what happened? We brought the CPU significantly down. And even if you look at the total parsing time, so for Airflow, what it does is you have a whole bunch of DAGs sitting in a directory. Every period, it'll cycle through all those DAGs, and it'll try to reparse it. You want to have your time about 5 seconds or less, total parsing time. When we first started, we had about 200 seconds. That's huge. We got it down to 5 seconds, and eventually we got it down to a second. So all of our DAGs were able to parse it down to less than 1 second. Now that's great. From a technology perspective, we did it. Our Airflow, we got our usage down, we got our DAG processing time down, but it wasn't enough. Now, here's where the operations kind of comes in. So what we noticed was you have these hundreds of DAGs, hundreds and thousands of these tasks that you have. What happened if a particular task we need to rerun, right? Or a validation didn't pass, you want to clean up and do it again. Through the UI, it was getting difficult for ops team to go find those particular tasks, or sometimes they accidentally click on the wrong one and run it again, force run. So that was introducing errors into it. So we helped them out. So we'll dive into a solution on that, but let's take a look at another problem that we had. When we first started ingestion in our account, we really had a very small subnet. Easy problem to solve, get more IP addresses. Yeah, that's what we did, right? We got more subnets. If you're familiar with Glue, each subnet gets tied to your Glue connection. Okay, that's pretty easy. You have Glue, you can have more connections. Yeah, that makes sense. We did that. You have one connection, one subnet, just have more Glue connections, attach it to your Glue. Fantastic. What problem did that introduce for us? The Glue, way it prioritizes a connection, let's say if you have S3 connections, it'll pick the first one, and it'll look at if it has an IP address available, right? And it'll run it. If a Glue job errors out, it will run it in the same subnet. So that didn't help us scale, if you want to do 2,500 jobs in concurrently, didn't help us scale that. We'll dive into how we achieve that. So our second try at the orchestration and the load balancing. So first thing, initially we had one Glue job, multiple connections to it. We switched it up other way around. We have multiple Glue jobs, one connection. Each connection going to different subnet, so different allocation of IP addresses there. A load balancer. We have our own load balancer in the middle there. So Airflow tells us, okay, run X number of jobs. Our load balancer looks at it and says, other way around, which subnet has the greatest amount of IP address available? It'll send the job there first, and so on, so it keeps going. So what did that really help us achieve? We were able to get 2,500 concurrent jobs. Now, of course, you'll have to talk to your account team to get some of those bumps into your service limits, and you will hit, at this scale, a lot of service limits. But account teams are your friends, SS are your friends. Talk to them, they'll help you through this. The other thing I want to mention is, remember the problem of accidental runs I talked about with Airflow that we had? Well, we introduced a DynamoDB database where we tracked each and every single run, each and every single task. And that even if you accidentally send the payload again and try to execute it again, it'll just simply say, okay, it's successful. You don't need to run it again. Now again, going back to the Mark's quiz, that helped us achieve the 100 terabytes a day. Now for that, I'll hand it back to Amy to talk about some takeaways.
Whew. So that's a lot of information that we share. So let me just summarize from the technical perspective what we discussed. First, in the cloud migration, security is first. We mentioned about we want to encrypt our data with the standard data encryption in transit and at rest. In addition to that, we added the data protection, right, for our sensitive data. We also talked about data access, and these take time. But if you do this homework early, it will pay off. Second, select the right tools. Mark mentioned about we initially thought about using DMS, but with the volume of data that we have, we choose Snowball. So make sure that you have the right tools for the right job. Automate everything. We cannot emphasize enough about automation, especially on these large data volume, where we need to do not just moving the data, but then we also need to do some basic transformation and encryption. And Sam mentioned about continuous evolving frameworks based on the need and then the throughput that we are looking for. And lastly, watch out for the AWS service limit. We mentioned about the IAM roles on the Redshift, and Sam mentioned about the IP address limit and API limit. So with that, I'm going to hand it back to Mark for the key takeaway.
Thank you, Amy. So migrating data to the cloud, as you can see, is not easy, right? And there's really no playbook that works across different organizations. So each organization has its own unique risk appetite, technology stack, and culture. However, some of the best practices that we share here today can be leveraged. So as I mentioned earlier, big migration starts with small steps, right? So these critical steps that we took really set the tone for the rest of the migration. So of course, we had that organizational driver, right? The acquisition of the Bank of the West. And we had this one team mentality. It really takes a village to migrate data to the cloud. And we had worked closely with Bank of the West teams, BMO teams, and AWS professional services team and product teams, because we're pushing the products to their limits, or even beyond their limits. And we chose the right tools for the job, and we built automation and repeatable frameworks on top of them. And last but not least is we had to set the right goals, right? So the goal of 1.8 petabyte of data, leave no data behind. And looking ahead for BMO, this migration really accelerated our cloud journey. And we are reusing and maturing a lot of these capabilities to accelerate our data migration to the cloud. And Jason Dow on my team earlier this week gave a couple of chalk talks about how we're reusing and maturing our capabilities. And the other piece is that we're leveraging data share, which is sort of a new capability that Amazon is offering, to maximize our data. What I mean by that is we want to have one copy of the data in the cloud, and we want to have proper governance of that data. And with data in the cloud and with proper governance, then we can accelerate our innovation in the cloud. So thank you guys for listening to our talk today, and I will turn it over to Felicia and the team for a Q&A.
All right. Thank you, everyone.